Well, greetings, mathletes, and welcome back. We're going to be talking about inverse functions today. Now, inverse functions are kind of an interesting little beast. Um, First of all, not every function has an inverse, but really what they are is they're undoing functions. We saw a little bit of this at the end of the last lecture, where we composed a couple of functions and we got x back. Well, we're going to take a little closer look at that, a little more of a theoretical look at that. One of the things that we want to remember as we're going through all of this is that all of the properties of inverses come from the fact that what you do to find one is swap your x and y coordinates, right? That's going to be a common theme throughout this whole thing. So let's go ahead and start a little bit with the theoretical side of things. We're not going to do it too formally, but I'm going to draw some good arm waving pictures to so we can try to understand what the theory is behind it and why we do what we do. And then we'll go from there and take a look at some examples. So let's go ahead and get started. Okay, so first of all, let's give ourselves a color here. Excuse me. Let's say I have a function. Ooh, this is a messed up function, but that's okay. Right, we got that. Well, my handwriting, my drawing is not so great today. That's okay. We'll take care of it right now. There we go. Okay, so we have some function. Let's call this function f. Right now, what f does is it takes an x value, right? Let's say that well, actually, let's give it a number. Let's say that in this case, the x value is 3. And without knowing what the function f actually is or any of the computations that go along with finding the function values, I'm just going to make one up, right? So let's say f, when you put a 3 into f, it spits out a 5. Okay, now the idea of an inverse function is if you compose them, if you run it through another, if you continue to run it through another function, right, that other function will undo what you just started with. Right, so if the function f takes 3 and maps it to 5, then its inverse will take 5 and map it back to 3, right? Now I'm not going to use the notation for an inverse function just yet. I'm just going to call this function g, just for ease more than anything else. And let's go ahead and draw that. And there we go. All right. So if g is going to get us back to what we started with, that means at the end it has to spit out a 3, right? That has to be the final output. And for that to happen, the input has to be a 5, right? So let's look at what this means. That means in the function f, I have the point 3, 5. But in the function g, the input is 5 and the output is 3. So I have the point 5, 3. And just from this diagram, you can see why it's just swapping the x and y coordinates. So now if I actually compose these two, f takes the function from 3 to 5, and then g takes the function from 5 back to 3 again. So it just undid everything f did. Now, if a function is truly an inverse, the notation for that, and this time I'm going to give it a name, we call it the name of the function that it inverts, right? So we'll call it f. And I do want to point something out here to note, excuse me, to indicate that it's an inverse. What we do is we write a -1 in the exponent place over the function. So f inverse looks like this. Right? I want to make sure that you really understand this. That -1 is not an exponent. That is a symbol that indicates that you have an inverse function. I know it looks like an exponent. In some very specific cases, the inverse happens to be the same as the reciprocal of the function. But that negative exponent does not mean to divide like it normally does. It's not an exponent at all. It's just telling you that it's a function inverse. So anytime you see that on a function, it's an inverse function. If you want to talk about 1 over the function, right, if you actually want to give it an exponent, what you do is this, right? And that would equal 1 over f of x. This is a function in and of itself. This is the inverse of f of x, and that is not the same as the reciprocal. Okay, so those are two different notations. It's a common point of confusion, so I wanted to make sure I pointed it out. All right, so having said that, get that off of there. Let's look at a couple more points. So let's say instead of 3 and 5, I pick something arbitrary. I say, okay, well, let's plug in A. So that means A goes into F. Let's say it spits out B, right? So that means that the point AB is part of the function F. Well, if this F inverse is truly an inverse, it has to take a B and map it back to an A, right? So that means that the point BA is part of the inverse function. Again, the x and the y just swapped positions, right? The value for x became the value for y, and the value for y became the value for x. So they just swapped values. Now, that whole swapping of x and y is actually how we're going to compute an inverse. Okay, so let's take a look at the computation of an inverse. This is just kind of describing what happens and why we're going to do what we're about to do. Okay, so let's say I have a function, and we'll just call it f for lack of a better letter. In any case, let's say that function is 3x minus 5. Okay. Now, if I want the inverse function, these are the steps that I follow. So, and these are going to be the steps no matter what the function is. It's just some of them get a little complicated. But with linear functions, these aren't too bad. So I like to start just by writing the function as a relationship between x and y, right? So I throw my y value in there. Now, to find an inverse, we swapped x and y. And so that's what I'm going to do. I'm just going to change the y, put an x in the place of the y variable and a y in the place of the x variable. So I'm directly swapping out x and y. Okay, so I have that now. Now, what we want to do here, if we want to find the inverse function, is we take whatever this expression ends up being, and we solve for y. So we just get it so it says y equals. So let's see here. It looks like y is already over on the right-hand side, so I'm just going to move everything to the left-hand side and then swap it around. So that means I can add 3 to both sides, right? And that gives me x plus 3 is equal to 3y. Oops. I'll just warn you, I have this terrible habit of saying 3 and writing 5, or saying 5 and writing 3. I don't know where it came from, but I keep doing it. There we go. That should be a 5. And so should that. There we go. Let's try this again now. So it's plus 5 plus 5. And then from here, at this point, I just need to divide everyone by 3. So I have x plus, I almost did it again. X plus 5 over 3 is equal to y. I honestly have no idea why I do that with 3s and 5s. It's the only numbers I do it with, and I've done it consistently throughout my entire life. So in any case, this expression, once I have this saying y equals, that should be my f inverse. That means that f inverse of x should be x plus 5 over 3. Okay, so we want to make sure that we actually have the inverse here. And so there's a test for it. In fact, the test comes from the definition of what an inverse is. Let me write the definition here, and then we'll look at the test. So f inverse is the inverse of f if, actually, I'm going to put two F's on that if. That stands for if and only if, meaning that it's a definition. If and only if f composed with f inverse of x is equal to x, and notice I said and, that means both of them have to be true. F inverse composed with f of x is also equal to x. Now we saw that in the last couple examples we did in the last lecture, right? We saw a couple of things that when we composed them, we got x back. What that means is that those were inverse functions of each other. All right, so let's test this. So what I want to do now is I want to take f and compose it with f inverse. And so we're going to check. So let's see here. F takes its input, multiplies it by 3, and then subtracts 5. I am putting f, what I think is f inverse in here, right? That's this. So let's put it in and see what it does. So that's 3 times x plus 5 over 3 minus 5, right? I can cancel the 3's here, and that'll give me x plus 5 minus 5, and then plus 5 minus 5, those guys kill each other, and I just get x. And that's good. That's what we want to see. Now, I'm going to back this up just a little bit because I want to make some more room. Right? So that's a check. That one worked. Let's check the other one now. Right? We want to check f inverse composed with f. We'll do it the other direction. So that means that f inverse, let's see where to go. It's down here. Takes its input, adds 5, and divides it by 3. Well, the input is 3x plus 5. So I'm just going to write that in. Notice I didn't write the f of x in there first. You can do it this way. I'm going to start skipping a few steps here and there as we've covered them already. Oops. That's a minus. Okay, right? So now, if I start simplifying, I get negative 5 and plus 5 cancel out. So that gives me 3x over 3, and then from there the 3's cancel out, and so I get x. And so once again, I've met the condition, which means these are truly inverses of each other. Okay, so that was a bunch of stuff. Let me walk through it one more time, just so we understand what we're actually doing. Okay, so first of all, we start with our function. Right, here's our function over here. We wrote it in terms of x and y, right? So I didn't have an f of x in there. Then I swapped the x and the y values. That gave me a new equation. And then from there, I solve for y, which is all these steps, right? Until I get here. And that tells me, that expression right here tells me what my inverse function is. So it's going to be the same thing each and every time you do this. You get your function, you swap x and y, solve for y again, right? That should be your inverse. Then to check it, you just need to compose it both ways. So you need to compose it this direction and this direction. Now, I'll tell you, in your homework, there's going to be some problems that only ask you to check to see if they actually are inverses, right? Basically, if you don't get x both directions that you compose it, then they're not inverses of each other. They have to get x each and every time. The input has to match the output. So if you don't get that, then they're not inverses. If you do get x both ways, then they are inverses. And so it's a real simple test to see if two things are inverses of each other. And then you'll have other problems that ask you to actually find the inverse, which is this process here, the swapping of x and y. Okay, now what gets complicated is sometimes these functions aren't overly nice, and so you have to massage them a little bit to try to find the inverse. So that's more what we're going to be focusing on today, is the little algebraic tricks that you have to use to actually find inverses. Okay, so let's go ahead and clear that off and look at another example. Okay, and this one's going to be for you to try. So let's say I have, let's switch back to different color here, shall we? Let's do that. Okay, and we'll try this again. So let's say f of x is equal to 2x plus 7. So, one, I can tell you that an inverse exists, and let's go ahead and find f inverse of x here. So, just remember, quick rundown, you're going to rewrite it in terms of x and y, swap the x and y, solve for y again, and then whatever y is equal to should be your inverse function. Okay, so see how you can do on this one. Go ahead and pause it here and see if you can work it out, and then we'll work it out together. All right, so I'm assuming you've paused it at this point. And so let's see what we got. So we rewrite it in terms of x and y. Okay, keep in mind, once you understand what's going on, you can jump straight to the step where you've swapped x and y. There's no problem with that. You don't have to write in every little step. These are just so you can see more or less what's going on. Okay, and now we have to, once we have this, we can swap our x and y, and then get y by itself again. So let's see, we'll subtract 7. Let's see if I can keep my sign straight this time. So now we have x minus 7 is equal to 2y, and then we'll divide by 2, and that leaves us x minus 7 over 2 is equal to y, and that y should be my f inverse. So that's x minus 7 over 2. Right? Keep in mind, you can split that up over the denominator. Right? You could rewrite it as x over 2 minus 7 halves, or you could write it as 1/2 x minus 7 halves, right? This way you can actually see the slope and the y-intercept very clearly here. But this is the inverse function. All of these are just different ways that you could write it. Later on in math, it's quite common to have to find the inverse function and then massage it and rework it so it's in a form where you can deal with it a little bit easier for whatever your purposes are. But for right now, we're just trying to find it. So this is actually a perfectly sufficient answer. There's nothing wrong with that. And, again, I've said this before, but every extra step you take is another place where you might make a mistake. So if this is an acceptable answer, this top thing, there's no point in massaging it more, to another correct answer, because you're just taking a risk of actually making a mistake somewhere and typing in the wrong answer. Okay, so we have that example. Now you could also verify this just by composing these two the same way we did before. I'm not going to go through every example of that just because what do you call it? It's going to take up extra time, and you guys can do that now on your own. So, okay, so let's take a look at our next example. So let's change it up. The last two we've looked at were linear functions. Let's look at something that's not linear. Let's say f of x is equal to x cubed plus 1. Okay? Now this is one of those ones, you have a cubic function in there. And so at some point you're going to have to undo that cube. And the only way to undo a cube is to use a cube root. So your answer, your inverse function, should have some kind of a cube root in it. Otherwise, you wouldn't be able to undo that cube. Okay, so right now, if you feel adventurous, and certainly it's not going to hurt you to try it, go ahead and pause here and see if you can walk through that. Right, just thinking about undoing each layer as you go. What does it take to undo the next step? But yeah, see if you can work it out on your own. We're going to work this out together right now. But if you pause it first, you'll probably watch the solution with better questions in your head. Okay, so in any case, let's go ahead and get started here. In fact, let's switch colors just because. Okay, so we start with the y equals x cubed plus 1. If we swap x and y, that gives me x is equal to y cubed plus 1. Very common mistake I see is when you swap these, you end up swapping it by writing x cubed equals y plus 1. That's not how it works, right? Because this is an operation. That's not actually part of the variable. So it stays in place. Now, we have to get y by itself. So we're going to subtract 1 from both sides. And that'll give me x minus 1 is equal to y cubed. Now, if I want to undo a cube, I use a cube root. Right? And a cube root cancels the cube. And so what I'm left with is the cube root of x minus 1 is equal to y. And that is my inverse, right? So my inverse is the cube root of x minus 1. Oop, cube root. There we go. Now, since we haven't actually composed these to verify, let's just look at what it looks like if I go ahead and compose these. So let's look at f composed with f inverse and f inverse composed with f. We'll look at each one of them separately. So if I do f of f inverse, that's going to give me, let's see here. So f cubes its input and then adds 1. In this case, the inverse function is the cube root of x minus 1. Okay, so this is what we're dealing with. Now, if I look at this, the cube root and the cube cancel each other again, and that leaves me with x minus 1 plus 1. Well, minus 1 plus 1 is 0, so this ends up being x. So that one works. Let's try it the other way now. So this one is going to be f inverse composed with f. And f inverse takes the cube root of 1 less than its input. Right? It looks like that. And the input is f. And so that's this. So I'm going to put in an x cubed plus 1. Now, if I start to simplify this, well, these parentheses don't have an operation attached to them. They're only there to show you where that function is. So plus 1 minus 1 will kill each other. And I end up with the cube root of x cubed. And once again, the cube root kills the cube. And I end up with x. And so once again, that verifies. Right? So it's a little bit more work, but usually if there really are inverses of each other, they collapse very quickly. Right? Okay, so that's dealing with a cube or a cube root. Now keep in mind, if this was the function, in fact, let's do that as our next example. We're going to take this function here as our original function and see if we can find its inverse. Okay, so let's go ahead and get this off of here. So we'll do that, and then a little bit of this. Okay. Now, instead of this being an inverse function, we're just going to say that's our function. And we want to find f inverse. Right? So we're looking for that now. So again, this is how you're going to deal with cube roots, or actually any root. We're going to start by swapping that x and y, and I'm just going to skip the step where I substitute y for f of x at this point. So it's going to be x is equal to the cube root of y minus 1. Okay, so we need to get rid of this cube root, and to get rid of a cube root, in fact, you don't just erase it like that. Darn it, wrong color. There we go. And to get rid of a cube root, what you do is you cube it, right? And so cubes and cube roots kill each other, but we have to put a cube root over here too then. So now we have cube root of x is y minus 1. Cube root of x. No. I did that completely wrong. The cube of x. There we go. Right, we cubed both sides here. So the cube of x is equal to y minus 1, and that just leaves me to add 1 to both sides. And I end up with x cubed plus 1 is equal to y. So that means I get x cubed plus 1. Now, if you remember, x cubed plus 1 was the original function that we were after. So the inverse of the inverse is the original function, right? So when you have two functions and one of them is the inverse of the inverse actually travels both directions. You can use them either direction and they work. Okay, so let's go ahead and clear that and we'll look at our next example. Okay, now these are the ones that they actually cause a little more problem than other functions. Well, let's just take a look. We'll see why real quick. So let's say f of x is equal to 2x minus 3 over x plus 5. Okay, so the first problem we run into is that when we swap x and y here, I end up with y in more than one place, right? So here, if I swap x and y, what I end up with is x is equal to 2y minus 3 over y plus 5, right? And we need to solve that for y. So if you have an idea, I think it's a great idea just to pause it and poke around at this thing to see if you can come up with the inverse. It may take a little work if you haven't seen one of these before. If not, that's fine. If you don't feel adventurous, let's just go ahead and look at the explanation. So I'm going to give myself a little room here. And I'm going to say x. I'm just going to rewrite the problem up here. So 2y minus 3 over y plus 5. Now, first off, we have a fraction, right? We have fractions on both sides, which means we can cross multiply. If I multiply this way, what I get is 2y minus 3, right? Because it's 1 times that numerator. And if I go the other direction, I get x times y and x times positive 5, right? So it's if you don't want to distribute it first, it actually looks like this. It would be x times y plus 5. But there's no reason, once you understand what's going on, that you can't distribute as you go. And then we would distribute this x. So now we have 2y minus 3 is equal to xy plus 5x. Okay, so remember what our goal is here is to get the y's in one place, right? You want it down to a single y so that you can say y equals this expression in x. So we need the y's on the same side, right? So what I'm going to do is I'm going to go ahead and subtract xy from both sides. And that's going to transform this to 2y minus xy minus 3 is equal to 5x. Okay, now the 3 is the odd man out. I have a y as a common factor here. In fact, that's where I'm going to be able to get a y by itself. I want to put everything that doesn't have a y back on the other side. So we'll do this. So that gives me 2y minus xy is equal to 5x plus 3. Now, I'm going to write the next step up top here, just so we can see it, because this is where the magic happens. Once you have all the y's on one side, every term that has a y in it needs to be on one side, and then every term that doesn't have a y in it goes to the other side. So you end up with this, right? 2y minus xy is equal to 5x plus 3. I'm going to take this y and I'm going to factor it out. So that leaves me with 2 minus x. What I'm going to do now is just divide both sides by 2 minus x. What that leaves me with, since this cancels, I have y is equal to 5x plus 3 over 2 minus x. And that is my inverse. But you can see it took a lot of work to get there. We had to use several tricks. So let's look at those tricks one more time just to make sure we understand what happened here. Okay, so when we have y in more than one place in an equation, right? And it's a factor in more than one term. The overall goal is to get all of those y's onto one side together so that you can factor them out, right? And you're trying to do it without having a y in a denominator. You want all the y's in a numerator if you can help it. And so we cross multiply to get those things out of the fraction. Then we distribute everything we can so we have everything out into separate terms. And then we start sorting the terms, right? We want to sort them so all the y terms are on one side and the non-y terms are on the other side. And that's this step. And once we get there, right, what we do is we factor the y out of all the terms that have y in it. And by doing that, we can get a single y, and we can divide off everything that's left to give us our inverse function. Now, verifying that these are inverses is actually quite messy. You can see because I'm sticking a fraction into a fraction and all this other kind of stuff. So it really does get a little bit weird to verify these, but they're absolutely verifiable. Okay. All right. So I want to look at one more of those, right? Because that was kind of that if you haven't seen that before, that was probably a bit much. So let's try another one and let's see how you guys do with it, and then we'll walk through it together. So let's see here. Here's your function. Let's say f of x is equal to x minus 4 over 2x plus 3, and we want to find f inverse. Okay, so see what you can do with this. Go ahead and pause it here and see if you can find the inverse on your own. Okay, I'm assuming you've attempted it, so let's see how you did. So first off, we want to swap the x's and y's. So that's going to give me x is equal to y minus 4 over 2y plus 3. Okay, and now we need to get y's out of the denominator so that we can group them all together on one side, right? And so this is where we cross multiply. If I multiply this way, I get y minus 4. If I multiply this way, and this time I'm actually going to include the distribution at the same time, it's x times 2y, which gives me 2xy, and then x times 3, which gives me plus 3x. Okay, so we're looking at this, and we need to get all the y's on one side. So I'm going to subtract 2xy from both sides. That leaves me with y minus 2xy minus 4 is equal to 3x, and then we'll add the 4 over. Right? And that's going to give me y minus 2xy is equal to 3x plus 4. Okay, now, fortunately, we have both of the y's on one side now, right? That was our goal, is to get them by themselves on one side so that I can factor a y out. That's going to leave me with 1 minus 2x is equal to 3x plus 4, and this is where we divide by the coefficient of y, which is 1 minus 2x. And that leaves me with, since this cancels, y is equal to 3x plus 4 over 1 minus 2x. And so that ends up being my inverse. 3x plus 4 over 1 minus 2x. Right? And keep in mind, sometimes the signs are played around with on these. 1 minus 2x, it looks better if it's 2x minus 1. So this is actually the same as putting a negative out in front and changing the signs on the bottom. Right? That's actually the exact same answer, and it's just as correct. It's just a matter of what you want to do with it. So both of these are actually correct answers. This one and this one. Right? So either of those should suffice. Okay. So that gets us through all of our, all of our computation of inverses. Those are about as complicated as they get, and as long as you got through those okay, you're in very good shape. Okay, so I want to talk a little bit about some of the other things that happen with inverses. In particular, the geometric consequences of what an inverse looks like, and how do you tell from a graph whether a function has an inverse or not. So those are a couple of skills. They actually don't require computation. What they require is your eyes, right? You're looking at things so you can see relationships. That's what you're actually after. Okay, so we'll take a look at that here. Okay, so let's go ahead and look at a graph here. Okay, now I've gone ahead and put in this function. This is the function f of x equals x, or the line y equals x, depending on how you want to look at it. In any case, this is the function here, right? So this thing ends up being important when we start looking at the graphs together. What I want to do to start out with is just plot a function and then plot its inverse so we can look at what the relationship between these two are. So what I want to do here is I just want to look at the cube root of x. We'll take a look at that graph. Okay, so there's our cube root of x here. Make it a little bigger. Okay. In fact, let's make it a little thicker too. Okay, so there's there's x cubed. Now, the inverse of x cubed would be the cube root of x. Now, this doesn't have a cube root button, so we end up having to do it by using an exponent. Right? I'm going to use an exponent of 1/3 to be able to graph this. And if I graph this at the same time, let's make this one thick, and then I'm going to change the color a little bit. Okay, so we have a function and its inverse here. Notice the symmetry, right? There's a reflection, there's a very clear reflection across this line y equals x here. And it actually turns out that this is the geometrical relationship between all functions and their inverse. They will always have this reflection symmetry across the line y equals x. It's always true. So let's change the function up a little bit. What if instead of that we picked a line, right? It's 2x plus 5. Okay, so that's a line here. That's kind of interesting. Let's make this bigger so we can look at the whole thing. Okay, so we have this big old function, or this line here. We can see it crosses right there. Now, let's change this other thing to its inverse. Okay, so it was 2x plus 5, so it should be x minus 5 divided by 2. Right? That should be the inverse. If it really is the inverse, then when I graph this, what should happen is we should have something that is a reflection of this line across this line. Let's see what we get. Hey, and it is. If we fold if we pictured this as paper and folded it on the dotted line, these two guys would line up. It's actually it's true for most things. Trying to think here if I want to what do I want to do here? So in any case, this kind of symmetry here is actually pretty important. Now, what's interesting about this is when you do a reflection, all the y values turn into x values and x values turn into y values. So for example here, right, there's a point right here. It looks like it's about at -2.5, and that's an x-intercept. When I reflect it, that becomes a y-intercept, right? The x-intercept on, or excuse me, the y-intercept on the inverse became the x-intercept. The y-intercept on the function became the x-intercept on the inverse. And so the x and y are truly swapping places here. Now, we run into a little problem. I'm going to erase these two. Let's delete those. When we have something like x squared. There. Okay, so if I have something like x squared here, let's make it thick. What happens, and let's see if I can do this without getting an unfortunate zoom. What ends up happening when you take its inverse, you know, we go across this line here, but what you end up with is a function that looks like this, right? It does the same things. The problem is it's not a function, right? It doesn't pass the vertical line test here. Well, there's a way to tell ahead of time whether that's going to be a problem or not. The way you tell ahead of time if it's going to be a problem or not is you use a horizontal line test. So if a function does not pass the horizontal line test, it does not have an inverse. And this is how you use the horizontal line test. If you can draw a horizontal line and hit more than one spot on the function, right, just like we can right here, this means there is no inverse. Boy, this thing is, you have to write slow. Ay. Wow, that is awful. That says no inverse. Nonetheless, that means any function that you could do this with, there's no point in trying to compute the inverse. I know we use the square root to undo the square function all the time, but you notice we always throw a plus and minus in it, and that's to give us both of these values here, right? That's what the plus and minus does. It gives you the value above the x-axis and the value below the x-axis. So as long as a function only hits one point, no matter where you draw this, then it will have an inverse. If not, then it doesn't have an inverse. Now, let's go ahead and kill that. And I want to jump back over here. Now, a function, oh, there it is. I was going to say it didn't write for me. Let's try it one more time. A function has an inverse, I should say inverse function, if and only if, right? There's that double F if again. That means that what's coming is a definition. If and only if it is a one-to-one function. Excuse me. A function is a one-to-one function if, when you look at the graph of the function, no matter which horizontal line you draw, you only hit one function value. As long as this only intersects the graph of the function one time, then it's one-to-one. So this is one-to-one. If I do the same thing and I have something that it's still a function, right? That's definitely a function. It passes the vertical line test. But if I draw horizontal lines, it hits more than one place, and there's several areas where I can hit more than one place. So this is now not one-to-one, right? So you can tell ahead of time whether it's worth your time to go ahead and try to compute the inverse. If it's not a one-to-one function, there's no inverse function. Later on, like in calculus and things like that, there's a way to force an inverse function into something that doesn't have an inverse, but you have to exclude part of the value. Probably a good example, let me do this. I'll just get most of this off of here. A good example is, what do you call it? If we look at x squared and x inverse, or excuse me, x squared and the square root of x, right? Square root of x. It does actually reflect across this line here, but the only thing it's reflecting is the positive half, right? I can't give you the bottom half because it won't be a function. So this is one of those places where there's actually what's called a domain restriction. The domain is the set of the inputs, where we only consider the positive values here, right? Only look at the first quadrant, then I can force an inverse to exist. But if I look at the whole function, the inverse doesn't exist, right? Because I would have to put this bottom part in there, and that would make it not a function. So that's one of the geometric consequences. First of all, they always have this symmetry. Second of all, the symmetry allows us to test ahead of time whether something is a one-to-one function and consequently whether it has an inverse. So that way you can know whether it's worth your time to compute one. In any case, that pretty much covers what I wanted to get through today. So remember, with inverses, if you want to find the inverse function, you take your function, swap x and y, and solve for y again, right? That's how you find an inverse function. From the graphs, you can actually test to see if something has an inverse by doing a horizontal line test. If you can draw a horizontal line somewhere on that function and hit 2 points, it doesn't have an inverse, right? And that tells you whether it's a one-to-one function or not. It is one-to-one if it has an inverse. If it does not have an inverse, it is not one-to-one. So in any case, until next time, keep your pencils and your wits sharp.